As you might have noticed, homework 2 is out, due on October 26th. Midterm for the class will be next week. You should be able to take the midterm, submit it via Canvas. So there will be a period of 3 days within which you can take it. There will not be a lecture on Thursday next week. I'll also post this on Canvas. You can use this time, for example, for solving your midterm if you want. And as you might have noticed, that there is a query on Canvas regarding online posting of videos. In particular, I'm considering putting up the videos just on YouTube so that they are freely available to anyone and not just through Canvas. Of course, if it bothers anyone or someone feels that this might change how the way they participate in the lecture, or it might prevent them from discussing freely, then I will not do this. So if you have any concerns, feel free to send me an email, talk to me after the lecture, send me a Slack message, whatsoever. I'm not posting them right now, but yeah, I'll wait some time. But in case there are any concerns, please do let me know. Okay. That's pretty much it in terms of announcements. Any comments, questions?
Which 3 days are the midterm going to be on?
So I was thinking after homework 2, so Wednesday, Thursday, and Friday, in case, yeah, earlier I kind of announced Monday, Tuesday, Wednesday, but then I ended up extending the deadline for homework 2 a little further. Is that still okay with you? Or?
Yeah, sure, that makes sense, yeah.
Okay. I mean, I'm expecting the midterm to take roughly 2 hours to complete. You will have longer than that to submit it once you start. I'll try to figure out how to exactly create a timed assignment and then post this on Canvas as an announcement regarding logistics. But currently I'm thinking, yeah, so in particular, you can use the lecture slot on Thursday, October 28th to take your midterm if you want, maybe with a little more time. Okay.
Is there any way that there would be feedback on homework 2 before one of the days the midterm is on?
Feedback on homework 2 might be difficult because we may not have, I mean, in particular, I'm planning on releasing the midterm the morning after homework 2 is due. So we won't be able to grade it. If you want any specific questions and if you want feedback, feel free to discuss these in the office hours, or if you can submit your homework a little earlier and indicate some questions you might want feedback on, we can give that. Okay. But if it's submitted really on midnight on 26th, then it will be hard for us to give feedback by next morning.
Okay, got it. Thank you.
But feel free to discuss any specific questions you want, or if you submit early, we can give feedback.
Yep, makes sense.
Okay. Anything else? Okay. So let's continue what we were discussing last time. This is just sort of a recap of singular value decomposition that we discussed. So we saw that the real spectral theorem lets us a nice, sort of gives us a nice way of thinking about self-adjoint operators between a vector space V and itself. Not just a vector space, I guess, finite dimensional inner product space, so that we can define adjoints, and also we only discuss things for finite dimensional spaces. And singular value decomposition is is a way of sort of doing the same thing. I mean, it makes it almost as convenient to think about any linear transformations between two finite dimensional inner product spaces. Okay. So these are still finite dimensional inner product spaces. And let's actually say a dimension of V is some n. And let's say dimension of W is some number m, some finite numbers. Okay. And we saw the we can get this by just sort of applying the real spectral theorem for self-adjoint operators by considering these operators phi star phi, which maps V to V, and phi phi star, which maps W to W. These are both self-adjoint and sort of even positive semi-definite, which in particular is self-adjoint. And they have the same non-zero eigenvalues. I'm not necessarily making a statement about the zero eigenvalue. It's possible that one of them has zero as an eigenvalue, the other doesn't. And in fact, something stronger was true. We saw these kind of spaces W lambda and V lambda for every lambda not equals zero have the same dimension. Okay. And if we find an orthonormal basis of eigenvectors for, let's say, phi star phi, and let's say the R of them correspond to non-zero eigenvalues, all eigenvalues will be greater than equal to zero because these are positive semi-definite operators. And if, say, R of them are strictly greater than zero, then let's just arrange them in descending order. Let's think of V1 to VR as eigenvectors corresponding to the non-zero eigenvalues, and we define W1 to WR simply this way as phi of Vi divided by sigma I. So it's basically the image of Vi with little scaling so that some properties look clean. And then we saw that these things sort of behave like eigenvectors, the best and sort of as best as they can, because you're mapping the space V to the space W. So the image of V will never be itself because it doesn't even lie in W possibly. So the best you can get is something in W. And this gets you almost as well as it can. So the image of Vi is sigma I times Wi. And also it behaves correctly with respect to the adjoint, that phi star of Wi is sigma I times Vi. So these are sort of like eigenvectors, but there are two sets of them and they are called singular vectors. And the VIs are called right singular vectors, WIs are left singular vectors. Yeah, I mean, left and right, I don't always remember, but we'll see in a minute. So at least there is one way of thinking about it. And these sigma i's are called singular values. Importantly, notice that they are all non-negative. In fact, we define sigma 1 to sigma r as positive. Sometimes 0 is included in the singular value, and these especially are referred to as non-zero singular values. But in particular, they are not negative. Whereas eigenvalues can be. Okay. Okay, any questions about this? This is sort of what we talked about in the previous lecture. Okay. I'll also quickly remind you of the proofs because, well, the arguments are nice. So I stated three properties. The first was phi of Vi is equal to sigma I Wi. This is just a definition. We define Wi to be phi of Vi divided by sigma I. Right? For sigma 1 to sigma r, which are positive, so I can divide. Phi star of Wi, we saw this kind of writing out the definition of Wi, and using the fact that Vi is an eigenvector of phi star phi, you can just write out the definition, and the eigenvalue is sigma I squared, and then that's why we scaled by sigma I, so that it cancels once and you get sigma I times Vi. Okay. V1 to Vr are orthonormal. Well, these are orthonormal eigenvectors for the phi star phi. So because of the real spectral theorem, we do get that they are orthonormal. And also, this I sort of stated, but didn't quite prove, that W1 to Wr are also orthonormal. And I mean, the proof is the same in terms of what we did above. So the inner product of Wi and Wj is phi of Vi divided by sigma I, phi of Vj, sigma j. And we can use linearity to pull these out. Phi of Vi, phi of Vj. And now just use the definition of adjoint, that instead of applying phi on one of the vectors, we can apply phi star on the other. So you can just apply phi star and then use the fact that this is an eigenvector. So we get sigma I squared times Vi. Now Vi and Vj are orthogonal if I is not equal to j. And if I is equal to j, then so this expression will be 0 if I is not equal to j, and 1 if I is equal to j, because, well, Vi has norm 1, and then sigma I is equal to sigma j. So you'll just have sigma I square, which will. You can also check that these are in fact eigenvectors of phi star. So we sort of defined this a bit asymmetrically. We said we start with eigenvectors of phi star phi. Oh, sorry. These are not eigenvectors of phi star. Phi star cannot have eigenvectors. These are eigenvectors of phi star. So we said we can start with eigenvectors of phi star phi, define the Wi's. The V's were orthonormal, the Wi's we proved were orthonormal. And now I'm also saying they're eigenvectors of phi star. You could have just done the whole thing in the other direction, started with eigenvectors of phi star, called them Wi's, defined the Vi's in terms of this property, and then proved that the V's were eigenvectors of phi star phi. So you can go in either direction. The nice properties which we can finally state here are symmetric, that phi of Vi is equal to sigma I Wi, phi star of Wi is equal to sigma I Vi. The V1 to Vr are orthonormal. They are eigenvectors of phi star phi. They can be completed to a basis if you want, but these are the ones that will correspond to non-zero eigenvalues. W1 to Wr are also orthonormal. They can be completed to a basis of the appropriate space, the space W. They will also be orthonormal, and these are the ones corresponding to non-zero eigenvalues. Okay. And we will see in a minute, they give us a clean way of understanding the action of the linear transformation phi. Any questions about these properties? So today we'll develop more on singular value decomposition, see what it means in the context of matrices and some applications. And the next couple of lectures, we will discuss some applications of the linear algebra we have developed so far. But before we go there, let's just go back to understanding what the action of phi is. And this is the linear transformation I defined last time, that you can just think of this as the linear transformation mapping V to W. And the way it acts is that for any vector U, it just takes its inner product with V and multiplies and scales W by this number. Okay. And we saw that this way of writing kind of works conveniently with the Dirac notation for writing vectors, which is why inner products have been denoted this way usually. So if you think of and write a vector U this way, then conveniently this becomes an inner product and you're left with the vector Wi. And that's what this transformation does. Okay. And the interpretation of this is kind of nice, that if you have phi, so let's maybe prove this. So let's check that this is indeed the case. I can write phi this way. Okay. Any questions before we go to the proof? Okay. So let's start with any vector U. Let's write it as so remember, V1 to VR form part of a basis of eigenvectors, an orthonormal basis of eigenvectors. And phi of U can be computed by linearity and we know what happens to the first R terms very nicely. There, we've already proved that phi of Vi is equal to sigma I times Wi. You just need to understand what this term is like. And I claim that this term is actually very simple. It's just 0. Okay. So we'll check this in a minute. For any I which is greater than R. And if we indeed have this, then we are done, because maybe let's do it in reverse. So let's compute what this linear transformation that we wrote here also does to the vector u, and I will claim that it does the same thing. So and because the v's are an orthonormal basis and each of these linear transformation will take an inner product with vi, all the terms where I is not equal to j and each of these terms are 0 if I is not equal to j and 1 if I is equal to j. So you can check that the only terms that will survive will give you exactly what we had. And so you'll be left with exactly the same expression. So both the linear transformation on the left, which is phi, and the transformation on the right do the same thing to every single vector. So they are the same linear transformation. So you can write it in this convenient form. The only thing I didn't quite prove was the fact that phi of vi is equal to 0. And this can be checked just by, again, using properties of inner product. So let's look at phi of vi inner product itself. By the property of the adjoint, I can write it as phi star of vi inner product with vi. And notice that phi star phi of vi is equal to 0 for I which is greater than r, right? This is only relevant for I greater than r. So the inner product of phi of vi with itself is 0. The only vector which can have inner product with itself as 0 is the 0 vector. And so we are left with the fact that this entire sum is just 0. Okay. So this is a convenient way of writing. In the real spectral theorem, we saw that you write a vector u as a decomposition ci vi. You replace vi by lambda I times vi when you apply the self-adjoint transformation. Here, you want to apply this transformation, you just replace vi by sigma I times wi for the first r positions where sigma I is 0 and is non-zero, and everything else is just replaced by 0. Okay. So it's a relatively simple way of understanding the action of any linear transformation between two finite dimensional inner product spaces. Any questions? Okay, if you don't have questions, I have a few. So few things to check as exercises. These are all very similar manipulations to what we have done so far, but I recommend trying them. It's just a good way of understanding the definitions and all the expressions involved in the singular value decomposition. So we wrote down an expression for phi, or how how phi acts. Similarly, you can write down an expression for phi star. As I said, the whole thing is symmetric with phi and phi star. We could start with either one of them. We just chose to kind of proceed in one of the directions. you can prove the same result for phi star. Just sort of the roles of VIs and WIs are now interchanged. Another thing to prove is just about this linear transformation, which we also called last time as the outer product of V and W. You can check that this is a rank 1 linear transformation. So its image is of dimension 1. Rank is just the dimension of the image. You can prove it directly, or you can think about the kernel, whichever is easiest for you. You can also check that the rank of the two linear transformation phi and phi star we defined is R. This, for example, gives you another proof that so if phi was a matrix, then phi star would be its conjugate transpose. And this gives you another proof that the rank of a matrix and its transpose, or row rank and column rank, are the same if you want. But of course, there are easier proofs of this fact. And then we'll also discuss one other proof later. And just also try to write the real spectral theorem in this language, that for a self-adjoint operator, we can write it again as a sum of outer products. Very similar to the one above, but here we have lambda i's, which are not necessarily non-negative. So they're real numbers, but not necessarily and maybe think a little bit about why we have to include what's different about this expression, so that we do need to possibly allow for negative numbers. Okay. And yeah, just in terms of remembering left and right, I mean, the way I usually remember left and right singular vectors, again, you don't really need to remember these names, but if you look at this expression for phi, then the VIs are on the right, and I called them the right singular vectors. The WIs are on the left. I called them the left singular vectors. So, and when you talk about phi star, the positions interchange, and so the left singular vectors of phi are the right singular vectors of phi star, etc. Yeah, it's in case you encounter these terms, but yeah, I'm not necessarily interested in testing your knowledge of the names, but more importantly, what they actually are or what they do. Okay, now let's go to matrices and see what singular value decomposition means in terms of matrices, how we can interpret it. And there are a couple of different ways of writing it, all of which you might encounter. So it's good to maybe be familiar with various ways of writing down the singular value decomposition. Okay. As usual, if we have a matrix, let's say with m rows and n columns, complex entries, say, then we can think of it as a linear transformation, because you multiply a vector by a matrix and you get another vector. So it's a linear transformation which maps the vector you multiplied to what you got. The vector you multiplied was in C to the n, it had the number of entries equal to the number of columns of the matrix. The vector you got had as many entries as the number of rows. And let's think of it as a linear transformation with, so these are vector spaces, and to define the inner products, let's just use the standard inner product on complex spaces. We have discussed, and then I can remind you if you want. Okay. And as before, now we will have orthonormal eigenvectors of phi star phi. Phi star phi is so adjoint of a matrix is just conjugate transpose. entry-wise conjugated times A. This is a matrix in with Cn, n cross n. So, and Wi, as before, can be defined as phi of Vi, which is just A times Vi divided by sigma I. So sigma i's, as before, are whatever are the eigenvalues for V1 to Vr. So if A star A will now be a positive semi-definite matrix is equal to sigma I, no, sorry. If you apply it to Vi, we know because these are eigenvectors, you will get some scaling. And we know because it's a positive semi-definite operator, you'll get some non-negative scaling. And we will call this sigma I square and then define sigma I accordingly. Okay. The outer product of W and V is a transformation such that when you apply it to U, you get the inner product of V and U times W. So another way of writing this outer product in the matrix case would be just W as a column vector. So as we discussed, we are always writing vectors as column vectors in the course by default. And so something is a row vector, we will either kind of state it explicitly or just say transpose. So W as a column vector. And V star, which is V transpose conjugate or V conjugate transpose. It doesn't matter in which order you do these things. And you can see that if you multiply it with U, so this is a matrix. And if you multiply it with U, you can multiply these two first. This is nothing but just the inner product of on complex spaces. So it gives you the same linear transformation that we've been talking about. And so you can write a matrix in this form. You can write it as summation sigma I, Wi, Vi star, or equivalently sigma I, Wi, Vi conjugate transpose. I going from 1 to R, where R is whatever is the number of non-zero eigenvalues of A star A or equivalently A star. Okay. And these are matrices. Has the right dimension. And it defines a rank 1 linear transformation based on what we assigned as an exercise on the previous slide. So this is one way of writing singular value decomposition for matrices. You can write a given matrix A as a sum of rank 1 matrices with coefficients which correspond to these sigma i's. Okay. Any questions about this? So this is just matrix A as a sum of rank 1 matrices, or outer products, if you like. Okay. There are a couple more ways of writing it more succinctly, just in matrix notation. It's the same expression. We'll just write it in 2 or 3 different ways, and you might see these in, depending on what book or reference you're looking at. So another way of writing it in terms of matrices is just a convenient expression which gives you what we wrote on the previous page. So you can think of a matrix in which these W's are columns. Let's call this matrix. Fortunately, this is also used, the letter you use is capital W for this. Hopefully you'll forgive me and distinguish this from the name of a vector space. The vector space here is C to the M and the C to the N. And let's think of a matrix V in which the vectors V1 to Vr are columns, and this is just a conjugate transpose of this matrix. So let's call this V star. And let's call this matrix sigma, in which the diagonal entries are just the singular values and all other entries are zero. So it's a simple diagonal matrix. So what we wrote on the previous page, you can check. If you multiply out these three matrices, you will get exactly the same expression, that this will give you summation sigma I. So it's just a succinct way of writing the same expression. Just use matrix multiplication to expand this out. These W1 to WR are orthonormal vectors. So the columns of this matrix are orthonormal. And V star is actually, well, if you think of the matrix V rather than V star is just kind of the rotated version of it. So columns of V are also orthonormal. Okay. So this is another way you might see of writing the matrix. It's just the previous expression written in matrix form. It's W sigma V star, where W and V are matrices with orthonormal columns. How many columns in each of them? Well, R columns for V. And so V star will have R rows. And sigma is a R times R diagonal matrix with positive real numbers on the diagonal, which are the singular values. So that's just a lot of times the singular value decomposition for a matrix will be stated in terms of this product rather than explicitly in terms of the eigenvalues or in terms of the singular values, etc. Okay. Any questions? Yet another way of writing down the singular value decomposition is by maybe puffing out these matrices W and V a little bit more. So recall that V1 to VR were part of this orthonormal basis for the space and these are W1 to WR are orthonormal vectors. We already proved in properties of the singular value decomposition. And you can complete them to an orthonormal basis. In fact, you can complete them to an orthonormal basis of eigenvectors for AA star. And yeah, you can think about why you can complete them to an orthonormal basis of eigenvectors. And now let's write the same matrices, but just kind of fill out additional entries so that W, the columns of W form an orthonormal basis. They're not just orthonormal, but there are enough of them to form a basis for C to the M. Similarly, the rows of V star or columns of V form an orthonormal basis for and sigma is now just a matrix filled with more zeros, so that the only interesting things that multiply give you exactly the same expression. This is just stuffed with extra zeros to make the dimensions match. So this now has n rows and n columns. Sigma has n columns, m rows. Wait, sorry, messed it up. M rows and m columns. Sigma has m rows and n columns, and this matrix has n rows and n columns. Okay. For a matrix in which the columns form a unitary, an orthonormal basis for the space to which they belong, it's called a unitary matrix. Just this property that the columns form an orthonormal basis. And so another way of writing the singular value decomposition, let me distinguish it from the previous one. You will write it as, let's say, now let me just denote V sub m just to say that this matrix has m columns. So sigma prime, which is the previous sigma, is a diagonal matrix with a bunch of zeros filled in the rest of the entries. Oh, sorry. This is the matrix of W's, and this is a matrix of P's. So this is yet another way of writing out the singular value decomposition, where now the matrices on the two sides will be unitary matrices. You've just kind of filled in extra vectors to make the columns an orthonormal basis in W and in P. And sigma prime is just filled with extra zeros, just padded, but it gives you exactly the same expression as before. So depending on what source you sort of consult, you might find one of these expressions for singular value decomposition. They're all the same. They're just a way of writing down how the linear operator acts. But yeah, you might see one or the other in literature. Any questions? Okay, before we start next topic, let's take maybe a 2-minute break. You can think about this. I'll be back in a couple of minutes, and then we can continue. Okay. Anyone think of any questions in the break? All right, so let's get to first application of linear algebra. I mean, we've seen some sort of small applications in between lectures, and we'll spend next couple of lectures on different kinds of applications. The first one, actually something that falls kind of right out of SVD, or singular value decomposition. It's called a low rank approximation of a matrix. So, and I mean, yeah, this has different names. It's also called principal component analysis, or PCA, for some special matrices that are derived out of data. And so, yeah, you might see these various names. What you are given is, let's say, some matrix A, m rows, n columns, complex entries. And let's say the rank of this matrix is some number R. Okay. The goal is to find another matrix B, same dimensions, such that this matrix B has possibly much lower rank. So the problem is interesting when K is less than R. Otherwise, well, you can always output A as an answer. Well, okay, for completeness, let's say k less than equal to r, although when it's equal to r, the answer is simple. And again, when it's greater than r, the answer is simple. And the goal is to have an approximation, or sort of B, we will think of as an approximation to the matrix A, in the sense that what remains after removing B, so A minus B, is kind of small, or is sort of like a small error. And so B captures the interesting aspects of A, if you want. Okay. And to define that A minus B is small, we need to say that kind of maybe A and B are close together in some sense, or the distance between A and B is small. And there are many notions of defining what a distance between two matrices is, or what does it mean to say that a given matrix is small or large. One way, which is, so just like for vectors, we defined sort of a length or a measure of how large or small that vector is. We can define a measure of how large or small a given matrix is. And so they're not just distances between matrices, but actually we will define for a single matrix what a norm or a measure of how large that matrix is, and the difference between the distance between A and B will be just how large A minus B is. Okay. And a measure we will deal with today is what is called the spectral norm of a matrix. And this is really inspired by just thinking of a matrix as a linear transformation. So A minus B is small if what it does to any vector is kind of small. So we are mostly interested in the action of this matrix, or what it does to a vector. And if it doesn't really change the vector too much when it, if it does, if it was 0, then you multiply it by any vector and you would get 0. And here we are just trying to say that when you multiply it by any vector, you get a small vector, then we will think of this matrix as small. Okay. So and the norm of a vector, or the size of a vector, we already defined in the inner product space. And here also A minus B is a vector, so we can write it as so we already defined the norm of a vector. This is sometimes called the 2 norm of a vector, and hence this 2 here. The one we defined using inner products is called the 2 norm. This is to distinguish it from many other ways also of measuring the size of vectors. But yeah, it's the distance, or it's the norm for vectors that we have been working with, which is just the square root of the inner product with itself. Okay. And so, of course, we divide by the length of the vector, or the norm of the vector, just to make sure that this quantity is not too affected by scaling. I mean, if I start with a vector of length 1, and if A minus B times V has length epsilon, then if I start with a vector of length 10, it can go up to 10 epsilon, that's fine. It just should not go much higher. So it's as a fraction divided by the length of the vector. Okay. Another measure of the distance between two matrices, or the norm of two matrices, or the norm of a matrix, is called the Probanious norm. So It's just defined in terms of the entries. And this is something which you will explore in the homework. So low rank approximation can be with respect to any valid notion of approximation or what it means for the approximation error to be small. These are just two examples, and there are many other ways we can define what it means for a matrix to be small or large. And we'll prove today that singular value decomposition gives a good approximation with respect to the spectral norm. In the homework, you will prove that it gives a good approximation with respect to the Frobenius norm. And in fact, more general results are also true, but we'll explore these two in the class. Any questions? Okay. And the solution to the low rank approximation problem, or the finding a good B, is actually just comes right out of the expression for singular value decomposition. So we saw that the singular value decomposition can be written as, the matrix can be written as a sum of rank 1 matrices, Wi, Vi star. And there are R terms if the rank of the matrix is R, okay, or the number of non-zero eigenvalues of A star A is R. And we just define B to be the first K term, the sum of the first K terms in this sum, in this expression. So instead of going from I equals 1 to R, you go to K, and just whatever you get, we will call this A sub K, and this will be our output, or this will be our, okay. And what I need to prove is that this gives a good approximation. So in particular, let's check what is the quality of approximation it gives, or how small is the error when I use this approximation or use this particular B. And we'll prove that what you get is the K plus 1th singular value. So in some sense, this is natural that we kind of took the terms involving the first K singular value. And so the error depends on the K plus first singular value, or the largest term we actually, or the next term which we did not take. And remember, these singular values, as before, we are arranging them in descending order. So sigma K plus 1 is smaller than sigma K. And we will also prove that this is the best you can do. So no matter what matrix you choose, if the matrix has rank less than equal to K for any B, then the error that you will encounter in the spectral norm, the two, or which we are denoting this way, is sort of the norm with a subscript 2 for the difference of for the matrix. The error will be at least sigma K plus 1. So the solution we gave, which is A sub K, is the best possible solution you can have. Okay. And as you will see in the homework, the solution is the same even for Frobenius norm, and in fact, more generally for what are called unitarily invariant norms. It's a theorem of, it's called the Eckart-Young-Mirsky theorem. But the interesting part is proving that this is the right solution, and well, what is the quality of approximation it gives us. Okay. So let's first prove how good is our solution. Let's just first prove that it gives us a value sigma K plus 1. Okay. Any questions, by the way, about what we are trying to prove? Okay. All right, so let's prove this. Let's first remember what the definition of the spectral norm is. Recall that the definition was And to prove that this is equal to sigma k plus 1, actually the quantity we are trying to study itself is a maximization problem, right? It's max over all v. So to prove that it's equal to sigma k plus 1, we will have to prove two things, actually. We will have to prove that it's less than equal to sigma k plus 1 for all v. And also, when we are saying it's really equal, what we are saying is there exists a v for which this inequality is tight. Okay, so we are also proving that okay. So let's first prove the inequality, and then we'll. Okay, actually, let's prove the inequality. And again, there are many different ways of proving this. Just kind of opening up the definitions of all the expressions that we have. Let's start with something we sort of studied so far. So let's say we have any vector v, which we can write in terms of this basis of v1, v1 to vn, which is an orthonormal basis. We saw what the linear transformation does to this vector. We saw that a times v is, you keep the first r terms. There you multiply by sigma I and replace vi by wi, and the rest is 0. We saw this for any linear transformation, in particular the one given by this matrix A. And the w's are orthonormal, the v's are orthonormal. So it's relatively easy to compute what happens. But before that, let's just also see what ak times v is. And ak was written as sum of the first k terms and you can check that what happens is exactly that you replace vi's by sigma I times wi's, but only the first k ones. And once you have this, the computation is, as before, a minus ak times v is equal to just and because the wi's are orthonormal, what you get is just similarly the inner product of v with itself is the sum of all i's. And as in the proof of Rayleigh quotients. And in fact, you can also write this as a Rayleigh quotient if you like. It's just a slightly more expanded way of proving this. But the ratio of the two terms look at this ratio, then the ratio of the two terms is, and now we use the fact that we have descending orders. So each of these sigma i's is less than equal to sigma k plus 1 square. Once you use the fact and the fact that the denominator is the sum of all i's, you will get that the whole expression is less than equal to sigma k plus 1 square. So that's just a quick proof. And as I said, this is only one of the possible proofs. You can prove it in any way you like, by going to Rayleigh quotients, by thinking of the matrix version of singular value decomposition, whichever you find easiest. As an exercise, think about the k equals 0 case of this. Implies that if you're just interested in the spectral norm of A, that's just the largest singular value. Okay. So that's a good thing to convince yourself of, or just check. It just follows from what we did. But so this is just an alternative definition of the spectral norm of a matrix, which we defined in this sort of maximization way, but it's just the largest singular value. That's another way of thinking about it. And it just follows from the computation we just did. Okay. I claimed that this is also tight. Can someone suggest a vector for which it is tight? I haven't asked a question in class today, so let me at least ask one. So, okay, there is an answer in chat. Yeah, VK plus 1. Yeah, so you can check that this inequality is tight for VK plus 1. You can either see it from the proof that the equality holds when all the CIs except for CK plus 1 are 0, and this will give you VK plus 1. Okay, so that's half of the low rank approximation part, where we proved that the error of our answer or our solution is sigma k plus 1. And then we want to say that the error of any solution is at least sigma k plus 1. So we didn't do too badly. I mean, in particular, the solution we gave is the best possible. Okay. To do this, I will need one fact, which is about just finite dimensional spaces, not necessarily even inner product spaces, just vector spaces, is that, and I'll leave it as an exercise, although I might include a quick proof sketch in the notes if you want, but try proving it, is that if you have subspaces S1 and S2, then first of all, S1 and S2, S1 intersection S2 is a subspace. And the dimension of this subspace is at least the dimension of S1 plus the dimension of S2 minus the dimension of V. Okay. You can do a little better, and in particular, even if V is not finite dimensional, but S1 and S2 are, you can still obtain an interesting inequality. But this is a kind of consequence, and this is an easier consequence to prove. So for now, yeah, you can assume that V is finite dimensional and try to prove this. Once we have this, the proof of, so once we have this exercise, then what we want to prove, because it becomes simple, in particular, we say that there exists a vector Z, which is in the span of V1 to Vk plus 1 and in the kernel of B. So B is any given matrix that we have. And let's just quickly see why this is. So the span of this has dimension k plus 1 because it's a span of k orthonormal vectors. The kernel of B, the rank of B is less than equal to k, so the kernel of B has dimension greater than equal to n minus k by the rank nullity theorem. Okay. And now, these are both subspaces of the n-dimensional space of complex numbers. So if we apply the previous result, we get that the dimension of this intersection is greater than equal to k plus 1 plus n minus k minus n. So it's at least 1. So there exists a vector which is in this span and is not equal to 0. Other than 0 is always in the intersection of these two subspaces, but a non-zero vector. Once we have this, what we need to prove is the spectral norm of A minus B is large. Recall that the spectral norm was the maximization over vectors. So this is just going to serve as a bad vector, which will prove that the spectral norm is large. So let's compute what is the norm of A minus B times Z. Now Z is in the kernel, so the second term just vanishes, and what we are left with is A times Z. And again, there are many different ways of doing this. Let's see one. Let's compute the square. So we can write this as the inner product of A times Z with itself. Using the definition of adjoint, we can write it as, let's see. Yeah, let's actually use what we did before instead of writing adjoints. So Z is in the span of the first k plus 1 of the wheels. So then we know what happens when we apply the linear transformation A. We get the W's. And because of orthonormality, we get that the only terms that survive is when I is equal to j. And because all the sigma i's are greater than equal to sigma k plus 1, we are just summing sigma I square for I going from 1 to k plus 1, and they are sorted in descending order. So all of these are greater than equal to sigma k plus 1. And this, you can check, is just the norm of Z squared. So, so in particular, the norm of A minus Z divided by the norm of Z is at least sigma k plus 1, which is what we wanted to prove anyway. Again, that's one proof of it. You can prove it using the Rayleigh quotients. You can prove it using Courant-Fisher theorem. You can prove it using properties of adjoints. So there are many ways of proving this. By now, the property, and they're all equivalent in some sense because we've obtained them from manipulations of some one basic property, but you can use whichever you find convenient. Let's see. Okay, I'll stop here for today. Next application will be related to it in terms of a least square approximation of data or dimension reduction of data, which we'll discuss in the next lecture. And as I said, there's also a related homework problem, which is about proving a low rank approximation in the Frobenius norm instead of the spectral norm, which we just defined. And let me remind you of the announcements. Homework 2 is out. And yeah, there is one problem on Frobenius norm. So now you know everything that you need to solve the homework. Midterm will be take home. We won't have a lecture on October 28th, Thursday. I mean, in an in-person class, we would have had midterm in that lecture, but you can still use that time. But also it will be flexible, so you can take the midterm at some other time if that's more convenient for you. And yeah, please let me know if you have any comments or objections or concerns regarding posting videos from lectures on YouTube, just publicly without, and not just to people on campus. Okay. All right, let's stop here. I'll stay on for a few minutes in case you want to discuss.